Start, sir.
Hello, let's look at another example problem involving two bodies. So we're going to look at a system where now two bodies are coupled through a set of cables, and we'll learn the process of applying the laws of dynamics to this system. Okay, so let's look at the example problem. The example problem here involves a spool. The spool has two pulleys on it. There's a inner pulley on which a cable is wound, and that is tethered to the top. The inner pulley has a diameter of radius of 0.5 meters, and the outer pulley has a radius of 1 meter. And what we are asked to find is the dynamical condition, the accelerations of the spool as well as a dead weight that is tied to the outer spool. So let's start drawing. Our first step is to draw free body diagrams. Like we said, if there is one skill you walk away from this entire 8-week class, it should be to draw quantitatively accurate free body diagrams. So just a set of simple assumptions. We assume the cables are massless, so they do not have an inertia of their own, and secondly, they only sustain tension. The second assumption is really not needed, but it is information you need to be aware of. Alright, so let us look at the dead weight first. That is the easier one to draw the free body diagram of. So I have a cable, and the whole idea of a free body diagram is to free the body 2 in this case of all external influences and replace the influence with simple forces. So I am going to call the tension in the cable 2 as T2, and so the only action that the cable has on this body 2 is to exert a force T2 on the body 2. Okay, and the weight is known, that is 64 newtons, and for all these problems I am going to assume G is 10 meters per second squared, as we said earlier on. We are not going to complicate the divisions. Alright, so we are going to assume this body has an acceleration A2. Now some of these several textbooks will show you what is called a kinematic diagram that shows the relationships between the two in a kinematic sense, and we will see how to do that in a short while. But for now I know this body has an acceleration A2, and I am going to, without loss of generality, assume it is downwards. Now the first law, the first Euler's law says sum of all forces is mass times acceleration, and I am going to take downward forces positive as my convention for this particular, for applying this law here, minus T2 plus 64, which is my W2, equals the mass, which is 64 divided by 10, times acceleration. Now in this case the acceleration is a scalar because we are only looking at one dimension of motion of this scalar. In this particular instance, the two forces under question, W2 and T2, both pass through the center of mass of this body. Therefore the second law of motion is somewhat trivial, it just becomes 0 equals 0. But I do want to write this down because in a general sense you would have to remember that there are two laws of motion when it comes to rigid bodies. So now for body 1, which is our spool, it's slightly more complicated. Let us draw the spool. The spool has an inner cable. This has a tension T1, and the tension in the cable has already, in the outer cable, has already been designated as T2. So there is a force T1 that acts here, there is a force T2 that acts here. T2 in general, let us, just to make a point clear, T2 is not equal to W2 because the acceleration of this body is non-zero. Okay, and the spool itself has a mass associated with it. The weight of the body is 32 newtons. So, we will use that. And I1, the moment of inertia of this body, is 4 kilogram meter squared. Now, we did not learn how to compute moments of inertia of various bodies. I am assuming you would have learned that in an earlier course in physics. A spool such as this is not a regular geometric body that you would have learned how to compute the moment of inertia, and it is not even possible to compute. In this particular instance, you are told what the moment of inertia is, because this number really depends on the masses of the two disks separately, and so it is like two bodies that have been attached to make a spool. So, one could not in a very general way calculate that from without being given that number. All right. So, we know we want to identify the center of mass of this spool, and let us say the acceleration of this spool is a1 in a downward sense. So, this is a1 is the acceleration of the center of mass of the spool. Let us be very clear. So, when we went from Newton's laws to Euler's laws, the first point we learnt is that Newton's second law is Euler's first law when applied to the motion of the center of mass. So, if I take downward force as positive again, it says T2. So, let me write the law first, and then this is Euler's first law. T2 plus 32, the weight of the body, minus T1 equals the mass of the body, which is 32 divided by 10 times A1. Okay, so, I am going to designate these equation numbers because we are going to come back and use them later. So, our first equation of motion came from Euler's first law applied to body 2. The second one is coming from Euler's first law applied to body 1. And now, we will look at the rotation of this body. So, let us say this spool has a clockwise angular acceleration alpha. The spool is one rigid body, and the point to understand here is that A1 and alpha, and as a matter of fact A2 as well, are related. Okay. So, the way we do this is, so let us first write this and then we will draw the relationship. So, if I take clockwise positive as my sign convention for applying the Euler's second law, and like we said, we will always choose the center of mass as our point about which we take the moments and the moment of inertia. The simple reason is you are not going, even if the center of mass is accelerating, sum of moments equals I times alpha, and this is a nice simple form of the equation to deal with. You do not have to remember the additional terms that arise when you are dealing with a point of reference that is moving in general. Okay, so, we are going to take moments about the center of mass. So, in this particular instance T2 times the radius associated with this is 1 meter, and the inner radius here is half a meter. We are given those numbers. So, the radius times 1 meter produces a counterclockwise moment, as you can see, and so by our sign convention that would be negative. T1 on the other hand produces a clockwise moment, so that would be T1 times 0.5. and the weight passes through the center of mass, so it does not create a moment, but I will still write that just for completeness. This equals I, which we are given is 4 kilogram meter squared times alpha. So, if I simplify this, minus T2 minus 2 T2 plus T1 equals 8 alpha, and that is my equation 3. So, let us quickly list out our unknowns. I have A1, A2 and alpha, T1 and T2 as the 5 unknowns, and we have 3 equations arising out of the applying the laws of dynamics to body 2 and to body 1. We still need 2 more equations. So, let us see what the 2 equations would look like. The first equation would come from studying this point of contact. So, if I now look at what is happening at that point of contact, and I will designate that as A. If this spool is unwinding an angle theta, then the center of mass will move down a distance r1 times theta, where r1 is this number 0.5. It is akin to a cylinder rolling on an inclined plane under no slip conditions. So, at this point A, there is no movement, there is no slip between the cable and the spool. So, the first equation, so the next we need 2 more equations. Let us and these 2 equations come from applying the laws of kinematics. Okay. So, at the point A, no slip would require A1 equals 0.5 times alpha. So, A1, the center of mass of this body 1 moving downwards, would have to exactly equal the rate at which that cable is unwinding. Now, if you look at the sense of the 2 quantities, sense meaning the directions I have chosen, alpha is clockwise. So, if alpha is positive, that would automatically result in positive A1. So, we have been consistent, but if these were chosen to not be consistent, say for example, if I had chosen alpha to be counterclockwise in this particular problem, then I would have to introduce a negative sign here to account for the fact that the sign of alpha is not the same as the sign on A1. Okay, so, this becomes our 4th equation. The 5th equation comes from relating the motion of 2 and 1 put together. So, if the point, so we will use the laws of relative motion between bodies 1 and 2. Okay, so I will just diagram of this to see what the spools do together, the bodies do together. So, if the angular acceleration of this body is alpha, then at this point A that we said, if the spool rotates an angle theta, then the center of mass comes down a distance 0.5 times theta, which also means A1 is 0.5 alpha. We have already done that. So, now the acceleration of 2, which is the point here. So, which is our point body 2 down here, which is moving down with an acceleration a2, equals a1 plus the acceleration of 2 as observed by 1, and acceleration of 2 as observed by 1 can be found from understanding how the spool works with the two cables. So, if this spool turns an angle theta, that also means that on the point B the cable winds onto the cable, winds onto the spool at distance r2 times theta. So, this it pulls up the cable at distance r2 times theta, that is acceleration of 2 as observed by 1 is r2, which is 1 times alpha. So, a1 is r1 times alpha and acceleration of 2 as observed by 1 is r2 times alpha. So, I can write this as a2 equals a1 minus alpha, which is our fifth equation. So, if we go back, we will quickly recap. We have equation 1 that came from applying Euler's first law to body 2, equation 2 which came from applying Euler's first law to the spool or body 1, equation 3 came from applying Euler's second law to body 2, to body 1, which is our spool, and the last two equations came from relating the accelerations, the angular acceleration of the spool to the linear acceleration of A1 of bodies 1 and 2. So, the net result is that we have 5 equations in 5 unknowns, the 5 unknowns being A1, A2, A3, T1 and T2. Okay. So, when you solve those 5 equations, these are 5 linear equations. In 5 unknowns, and the result, I am going to write the result, you can check this on your own time. Okay. Now, what you need to observe here is that our initial assumption of alpha being clockwise is correct, because alpha comes out to be 15 radians per second squared. A1 is positive, that is the spool is moving down, but A2 is negative 7.5 meters per second squared, which means that A2 the A2 is negative, means the body is actually moving up. Another, I mean, this is a way to kind of intuitively check the calculations that you have performed. T1 is a large number in comparison to T2, meaning T1 is greater than T2. That should also be obvious, because the cable 1 is bearing the weight of the spool plus the dead weight 2 in a static sense. So, when nothing is moving, the cable 1 is bearing both of those weights. So, it should you should be able to you should kind of expect this. I do want to close with one point, that notice that when we applied this Euler's second law to the spool, we chose to take moments about g, which is the center of mass of the spool. If you did that, if you did not do that, but chose to apply sum of moments equals I times alpha about any other point, you would get an incorrect answer, primarily because you are not guaranteed that those other points of reference are non-accelerating. So, the simplest choice, I will reiterate again, for applying Euler's second law is to ensure that the point about which you take moments and calculate the inertia, moment of inertia is the center of mass. We will continue this in another example problem next time.